Let's see, are we recording? Yep, we're recording. All right. Man, I gotta say, I was headed to the lecture room today, and I was headed across campus, and I forgot my computer. I used my my tablet or my Microsoft Surface to broadcast lecture, and I forgot it. And I was just getting ready to walk into Smith Hall, so I had to run all the way back and get it and come back. Because see, I don't use the instructor station here, but because they're kind of slow, and I got here late, and I still got everything up and running by in time for class. And I guarantee if I had used that station, I'd be still sitting there waiting for it to load. So I'm glad I made it on time. A couple quick announcements. So did everything work well with the homework, with getting that submitted? I know there was I don't know what happened with one of the settings, but I had said I wanted everybody to have multiple attempts at it. And for some reason, the setting didn't work for the first time for a couple students. And I literally just hit the refresh button, and that seemed to work. But I checked the one today. It should be good. So we're going to have a similar homework assignment today, due Monday, where you enter values and whatnot. And it'll be of similar length, maybe a little bit longer, but it's not anything that's terribly complex. So homework 1.1 was due today. Homework 1.2 is going to be assigned today, due Monday at 1 p.m. And I've got all the attendance grades and whatnot updated from the last time, so everything's good to go there. If last time was a physics review, today is a math review. We're going to review the math necessary for the class. Pretty much everything that you need to be able to do mathematically in order to negotiate the class as a whole. But what I'm going to focus on in the beginning, at least this is what your first homework is, or your homework 1.2 is focused on, is trig. Because if there's any one field that affects things right now, or at least starting this week, it's the trig. The algebra and the calculus, I mean, obviously that stuff matters, but the calculus really isn't going to come into play until later. And there are some specific algebra skills which will come into play soon, but really the trig's going to come up first. Okay, I want to go back to what we were talking about last time because I want to finish this example. It's really simple, but I want to go through this because this is one of the first tasks on your homework assignment that's due Monday, is to check whether something is dimensionally consistent. So what we've got here, and I brought this formula up last time, this is a very popular expression in the world of fluid mechanics. This is how we determine the total amount of energy in a fluid conduit. And it's a function of three terms, or three expressions. There's a fraction plus another term. Those terms are the pressure head, the velocity head, and the elevation head, respectively. And in the world of fluids, we actually measure energy in terms of its respective elevation. And so the idea is that these terms will all yield an elevation or a distance term, and we want to make sure that they're dimensionally consistent. And so what I mean by dimensional consistency is that if you're adding terms together, you can't really add meters to kilograms, or you can't add meters per second to meters per second squared. If you're adding terms, they need to be of dimensional consistency. You can add meters to meters. You can add pounds to pounds, etc. So we're going to see whether or not these terms are dimensionally consistent. And we've got a series of expressions and units to go along with those. So let me pull up the course notebook. Wrong keyboard. Okay, so this was me in structural analysis. Let me go to my statics notebook. Okay, by the way, has everybody been able to access the course notebook? I'm just curious. Okay, one of the things you'll notice, and this was brought up in another lecture earlier today, because I used this notebook for that class as well. If you go to the content library, what you'll see is a series of pages. Right now there's really only two. There's the unit conversion example and the dimensional analysis example. What I'll do is I'll ensure that each of our examples are on a new page. It won't be just one big old notebook, so you won't have to scroll through pages and pages and pages to find example 17. It'll be pretty easy to find. Okay, so let me get my little pen out. Let's full screen this. Okay, so what we're going to do is we're going to see whether or not this term is dimensionally consistent. And so let me rewrite this down here. Let me move this out of the way. So let's start off with just rewriting this expression. One thing you will start to find in engineering real quick is we have a propensity to use some of the Greek alphabet in some of our expressions. So we have the pressure divided by this lowercase letter gamma, which is the common expression for unit weight, plus v squared over 2g plus h. Okay? And what I want to do now is I want to go into each of these terms and I want to replace the terms with sort of their respective unit system. Okay? So what I mean by that is this. So let's start off with the first fraction. Let's start off with this fraction right here. Okay? So this fraction is a pressure divided by a unit weight. Okay? And so the way I'm going to write that is I'm going to say we have pressure divided by unit weight. Okay? And the pressure is expressed in newtons per square meters, and the unit weight is newtons per cubic meters. Okay, and there's a reason I'm writing it this way, because you can probably guess why. If you remember from, I don't know, probably algebra or whatnot, that if you're dividing two fractions, you can flip and multiply. Y'all remember that? So that's ultimately why I'm writing it this way. Let me see if I can squunch that a bit, because I'm going to run out of room, so bear with me. I'm going to rewrite that. So let's see. So we've got newtons per square meter divided by newtons per cubic meter. And so that's the same thing as this fraction, or as that previous fraction from a units perspective. Like whatever the values are, whatever the values I would plug into that expression, whatever the pressure is, whatever the unit weight is, etc., those would be the units that I would utilize. All right. What about the next expression? Okay. What about this? Well, okay. Let's look at this from a units perspective. Okay. From a units perspective, what I'm going to be doing is I'm going to be taking a velocity, which is measured in meters per second. I'm going to square that, and I'm going to divide it by this gravity term. And I'm going to talk about the 2 here in a second, but I'm going to be dividing it by gravity, which is measured in meters per second squared. Now, one question you might have is, why did I ignore the 2? Okay, why did I ignore the 2? Well, here's why I ignored the 2. Okay, let's take a time period, 30 minutes. What happens if I take 30 minutes and I divide it by 2? What do I get? 15 minutes, right? So if I take minutes and I divide it by 2, I get minutes, right? From a units perspective, that term doesn't change the units at all, right? Okay, so that's why I'm sort of ignoring the 2, because it doesn't really affect anything from a units perspective, okay? Because like I said, the purpose of this is to check and see whether the inputs and the outputs are dimensionally consistent. I care about the units. I'm really not concerned about the numerical scalar coefficients, if you will. Okay, and finally, we're going to add this term height, which is just in meters. Okay, so if you're wondering what I did, all I'm doing is I'm basically taking these terms here and just plugging them into the expression as it's written with their appropriate unit systems. Okay? Is everybody with what I'm doing so far? Everybody with me on this? Okay. So now what I'm going to do is I got a bunch of alphabet soup here. Let's see if I can simplify it a bit. Okay? I'm going to scroll down a little bit, which do me a favor. I'm really going to do my best to try not scroll up and down like crazy. But if for some reason I'm going too fast and you're like, whoa, Dr. Mike, we're still writing, please raise your hand and let me know. Because chances are, if you're still writing stuff down, there's probably 10 or 12 other people that are still writing stuff down. So definitely don't hesitate there. Okay. So let's start off with this first fraction. So remember, if you're dividing two fractions, what you can do is flip the second one and multiply the two fractions, right? So instead of newtons per meter squared divided by newtons per meter cubed, I can say newtons per meter squared times meters cubed per newton. With me so far? And then the same thing over here, I can say, now hold on, let's take this for a second. Let's look at this fraction. All right, I've got meters per second and I'm squaring the whole thing. Now why am I squaring the whole thing? Well, I'm squaring the whole thing because this is velocity and velocity was squared. So if I'm squaring the whole thing, I square both the top and bottom, so that first fraction becomes meters squared over seconds squared. All right, and then instead of dividing, I'm going to flip and multiply. Did that make sense? Everybody okay with that? And then plus meters. Oh, that's one too many humps on that. Okay. So now we can start looking at these fractions and doing a little bit of assessment. So this first group right here, what I can do is say the newtons cancel, and what do I have? I have meters cubed divided by meters squared. That comes out to meters, right? And what about this second one? I've got second squared over second squared. They cancel. Meters squared over meters comes out to be meters plus meters. So this expression, is it dimensionally consistent? Yes, it is. See, it wouldn't have been, see, here's the whole point. So first off, is this dimensionally consistent? Yes. So the question is this dimensionally consistent? Yes. All right. Where was the value in this exercise? Well, go back to the original formula. The original formula is P over gamma plus V squared over 2G plus H. What if I forgot the squared? What if it was just V over 2G? Would this expression have been dimensionally consistent? No, right? And so that's sort of the value here, is that if you're going through and deriving your own expressions or doing your own calculations, this is sort of a valuable exercise that you need to be able to take on the side in order to assess whether or not the math that you're doing makes sense. And if you think engineers don't derive their own expressions, you'd be wrong about that. I mean, as the bridge engineer in me, I can't tell you how many spreadsheets I've built where I've derived my own little formulas to make my life a little easier when I'm doing a bunch of routine calcs. And stuff like this is pretty valuable to be able to assess whether or not your answers are making sense. Okay, any questions? Okay, so on your homework, the first problem is you're basically given a similar type of expression, but what you're given is basically one pile of junk equals another pile of junk, and the question is to see whether or not those two expressions are identical in terms of their units, because you've got forces and masses and times and velocities and all that jazz, and you're supposed to check and see whether or not they're consistent. They may be, they may not. Okay, everybody good? All right. I want to talk for the rest of the lecture about the math that we do in here. And this is, again, really to just sort of set the stage for what we're going to be doing this semester. Okay? The reason that I think this is valuable is, one, first off, it's your first week. It's Friday afternoon, and I want you to sort of ease back into the semester. So relax. The rest of the lecture isn't going to involve any, hardcore computation problems or anything. But the other thing that I want to try and avoid is being this guy. I don't want to be the guy where the problems that we do in the class or on the homeworks are really easy, and then it comes to the exam and it's like, oh my goodness, this is so challenging. I don't want to be that guy. It's the guy I try to avoid. And one of the reasons that this happens, especially in this class, is I have found that a lot of times when we're discussing concepts in statics and mechanics, usually that stuff's pretty easy. That stuff's pretty straightforward to understand. the statics, the forces, the moments, the centroids, and all that. That's pretty easy. But in order to engage in those computations and in order to do those problems, you do have to possess some skills in algebra, some skills in trig, some skills in calculus. And that's the stuff that tends to trip everybody up, not the statics. It's all the stuff behind the scenes. So what I did is I basically went through the class and I said, okay, what skills do you need? Or what skills have tripped students up? And that's kind of what we're talking about today. Now, before I go into this, I do want to mention one thing, and it's completely fine for the first couple lectures, but you'll probably want to adjust later. During some of the examples, like I know that your smartphone and whatnot has a calculator on it, and that's fine for some of the stuff that we're doing in here, at least for these first couple lectures. But later on, we're going to be doing some problems in here that involves some more advanced stuff that your calculators need to do, like 2x2 system solution, 3x3 system solution, some trig functions, and so on and so forth. And so I would highly recommend that you bring your calculator with you, like that one right there. That is perfect for the class. The Casio calculator or the TI-30X, either one of those are fine. I don't care if you bring a graphing calculator. I know some of you had graphing calculators in high school. That would be fine too. But what I have found more often than not is that the apps on your smartphone usually don't have the capabilities. And plus, those apps aren't going to be allowed on your exams. Again, I don't care what calculator you use as long as it doesn't have a Wi-Fi connection. Yes, sir. I'm sorry. I thought I saw your hand raised. Any questions? Okay, so let's talk about the math in here. And I want to start with the algebra. First off, factoring. I know this seems really basic, or I hope it seems really basic, but we're going to need to be able to do this in here. So if you don't understand how to just factor stuff, that's something those are skills that you want to shake the rust off of. The quadratic formula, I mean, that's something that we'll probably solve every now and then, and you kind of need to understand how to do that. This is a big one, and I'll tell you right now that more often than not, I find that students have done this before, but it's just been a while, right? So let me go back in your memory bank. So let's see if you remember how to solve these types of problems. So with these types of problems, you've got two equations and two unknowns, and so the idea is to find the value of x and the value of y that satisfy both equations, right? And so there's a couple of ways of doing that. So for example, what we might do is we might multiply this entire equation by, 4, and this lower equation, we might multiply that whole thing by 3, so that we get 12y and negative 12y, and then we add the equations up, right? So this is like 15x and 8x, that's like 23x equals whatever that is, and you can solve for x and then plug that value of x in to get the value of y. Y'all remember that? Been a while, right? Okay, so that is a surprisingly common exercise in this course, okay? Because I'll give you an example, okay? Whenever we deal with two-dimensional static situations, the first statics problem, the first fundamental statics problem that we're going to be dealing with are what are called concurrent force systems, or if you go to the syllabus says statics of particles, okay? And that's just a fancy term for any situation where all the forces all meet at a common point, okay? And so that's a concurrent force system. A non-concurrent force system is when the forces don't meet at a common point, and so that's why we start developing the concept of moments. But when we deal with concurrent force systems, let's just say 2 dimensions, okay? In 2 dimensions, any scenario, any static system must adhere to the following 2 equations. The sum of forces in the x direction equals 0, and the sum of forces in the y direction equals 0. That ensures that the system remains static, remains in equilibrium. This is a course in statics. That's what we're trying to do. And so, more often than not, there are 2 unknown forces that keep that system in equilibrium, and we need to solve for those 2 unknown forces. 2 equations, 2 unknowns. So this is a very, very popular exercise in this class, and it's used more common than you would think. When we actually start doing this in here, I will show you how to do it. I will see if I can get actually the Casio app. There's a program that you can install on your system to actually bring up the Casio, and so we'll do it together. And I'll show you how that works. It's really not all that challenging. If you don't have a Casio, like for example, I see you have the TI 36X. The function is very, very similar. And if you have another calculator, I mean, these are usually pretty basic functions on your calculator, and you have two resources. You can go to YouTube, because there's probably plenty of videos on it, or you can come see me. I can probably help you figure it out. Okay. Any questions about the algebra? That's pretty much it in a nutshell. If you can do basic arithmetic and this stuff, you're probably good on the algebra. But you need to be able to do this stuff. Everybody good? Okay. Let's talk about trig. That is probably the most critical concept for right now, for the early part. So the first thing I want you to be able to understand is the basic structure of a triangle. So right up here on the top right, I don't care what the triangle looks like, the sum of the internal angles is 180 degrees for any triangle. So that's something that you just need to know, okay? We're going to be taking forces and adding them together in a tip-to-tail vector fashion, and in order to do that, we need to be able to solve triangles. So that's a fact that you need to know. You also need to understand just kind of the terminology of complementary angles and supplementary angles. So two complementary angles add up to 90 degrees. Two supplementary angles add up to 180. I have found that this diagram and understanding what's going on with this diagram is incredibly important. Can anybody point to this diagram and show me two angles that are equal? Yes?
You could do like 2 and 6 would be the same angle.
2 and 6 would be the same angle, yes.
1 and 4.
1 and 4, yes. In fact, in this diagram, there are only two unique angles because angle 1, angle 4, angle 5, and angle 8 are all equal. The same with 2, 3, 6, and 7, okay? That's actually hearkening back to probably your geometry class in high school. Remember proofs and all of that? Everybody's like, why did you bring up proofs? We were having a good day. I mean, really, did you have to do that on a Friday afternoon? No, but understanding that's actually kind of important. Being able to recognize that that geometrical riddle, I guess, would be maybe the best way of putting it. Because we're going to start adding vectors together, and then we're going to have to form forced triangles. And understanding this is actually pretty important. So, everybody good with that? Okay. All right. The basic trigonometric functions. Everybody remembers SOHCAHTOA, right? So, what is it? Somebody told me that was pretty funny. Some old hippie caught another hippie tripping on acid, something like that. I've got jokes. I've got dad jokes. I know. But yeah, it's just the mnemonic for remembering the computation of trigonometric functions, or the relationship between trig functions and a right triangle. In fact, I sort of think of trigonometry, the whole science, as really trying to connect three concepts. The first concept being this, the idea that trig functions are just the ratios of sides of a triangle. The second concept is graphing the trig functions, the sine and cosine being the wave sinusoidal function and the tangent, going like that. And then the third concept being the unit circle, the idea that the sine and cosine are just the x and y coordinates on the unit circle. The connection of those three concepts, that pretty much is trig. So, but that's off to the side. Okay, so first off, just being able to solve a right triangle is a pretty critical skill. Okay, if I give you, let's say, the length of this side and this angle, you should be able to figure out everything else, just period, okay? So, for instance, if I gave you this angle and the opposite side, you could find the adjacent side by using the tangent function, right? The tangent function is equal to the opposite over the adjacent, so you could plug and chug and solve for the adjacent, right? If you have the adjacent and the opposite, you could use the Pythagorean theorem to find the hypotenuse. And then remind me, if you have this angle, and you know this is 90 degrees, how can you find this one? What's the sum of all three angles inside a triangle? 180. So you can solve all of the unknown components of that triangle. Being able to solve a triangle is a critical skill. Okay, that I would argue is one of the most important aspects of the course. In fact, just the sort of the rules of triangles are that pretty much if you're given 3 pieces of information about that triangle, you should be able to solve for the other 3 pieces of information, right? A triangle is defined by its 3 internal angles and the length of the 3 sides, and given 3 pieces of information, you should be able to solve for all 3. All right, everybody okay with this? Any questions? All right, I would argue that this is sort of the same thing. If you had you probably covered this in what, like either pre-calculus or maybe calculus 2? Probably something, the relationship between rectangular and polar coordinates. I sort of think of this as a very natural extension to just basic trig functions, but this is pretty valuable because what we're going to do later on when we start adding force vectors is adding 2 vectors. We can just use a tip-to-tail fashion and use some fundamental trig to figure that out. But when we start having 5, 6, 7, 8 force vectors all at one spot, using a tip-to-tail vector addition method, which we'll talk about next week, would get really cumbersome. So what we're going to do is we're going to take those vectors and we're going to use a sort of special vector notation. If you ever hear the term IJK vector notation, if some of you maybe have had a later calculus course like calculus 3 or something like that, calculus 2, you might have heard of IJK vector notation. But basically what we're doing is taking a vector, splitting it up into its x and y components, and then adding up all the components. It's much more systematic. It's much more simple when dealing with multiple vectors all at once. And so all this is really just what was on the previous slide, just written in terms of x and y coordinates. So in terms of the coordinate system, you know that in 2 dimensions, there's sort of 2 standard ways of graphing a point, right? So if here's the coordinate system and there's the origin, I can go over x and up y, rise or run x and rise y to get to the point. I can also use a polar fashion. I can go out some radius and subtend some angle or rotate some angle theta and get to the same point. So being able to connect x and y to r and the subsequent angle theta is incredibly important. Okay, I've been talking a lot about vectors. That's going to be a significant topic of discussion next week. And I mean, the title of the textbook is Vector Mechanics. What defines a vector and what makes a vector special are really 2 things: its magnitude and its direction. And so a common mathematical way of describing a vector is to use polar coordinates because its magnitude is the radius and its direction can be defined by that angle theta. So it's a pretty natural concept to understand. All right, this one is going to show up real quick. So you want to sort of write this down. So the law of sines and the law of cosines. So when do you ever use the law of sines or the law of cosines? You use these expressions whenever you're dealing with a triangle that's not a right triangle. Okay? Whenever you're dealing with something where none of the angles are 90 degrees, because then the triangle has an irregular geometry. Okay? So basically the law of sines and the law of cosines are just generalized expressions of what we saw before. I'll give everybody a sec to write this because I kind of want to illustrate some things so that you're aware, because I think it'll be pretty important for solving this stuff later. And if I was a betting man, it's been a while since you've done this stuff, am I right? Some of you are like, oh man, you're bringing it back to like 9th grade or 10th grade. How long ago was it for some of you? I'm just curious. 9th or 10th is about right? Okay. What's that? I'm starting to get some myself right here. It's too early. I need to talk to somebody about that. I think mine started with parenthood. Like, don't fall down the stairs. That's how it started, you know. My wife and I, we live in a split-level house, so it feels like there's stairs everywhere, especially when you have a toddler that likes to resist the word no, you know. I'm just teasing. I love that little girl. Okay, I want to show you something. So, again, the key thing to keep in mind whenever trying to solve triangles is that in order to solve the triangles, you need 3 pieces of information to solve for the other 3. The law of sines is the most effective whenever you have opposing pieces of information. So, for instance, if I know the measurement of angle A and I know the length of side A, what that means is I'm going to know a third fact, whatever that third fact is. It might be the length of this side, it might be that angle, whatever. But whenever I have an opposing pair of information, the law of sines is going to be the most powerful tool, because let's say I know, I don't know, this side right here, okay? So I can say the sine of A over A, so I can say, all right, the sine of A over A equals the sine of B over B. And then I know everything in that formula that I just wrote except for angle B, right? So I can solve for angle B pretty easily, right? Multiply both sides by little b, take the inverse sine or the arc sine, and boom, there's my angle, right? And if I've got angle A and angle B, how do I find angle C? What's the sum of all those angles got to equal? 180, right? So 180, 180 minus the sum of those two will give me C, and then break out the law of sines again to figure that one out. Boom, done. All right? That's the most beneficial use of the law of sines. The law of cosines tends to work best. Let me erase all this. The law of cosines tend to work best when my 3 known quantities are all sort of lumped together. So, for instance, if I know this, this, and that angle, and I need to solve for the rest of the triangle, I can use the law of cosines to figure out, let's say, that side A. Because if I look at this term right here, let's say I want to solve that, just look at this equation. A squared equals that squared, I know that, plus that squared, I know that, minus 2bc, I know those, cosine of A. Boom. Just plug and chug, solve for little a, and now I've got opposites. Got opposites, break out the law of sines, boom, figure it out. Okay? Does that make sense? All right, any questions about that? So yeah, law of sines works best when you have an opposing pair. Law of cosines work best when your 3 known quantities are all sort of lumped together. Everybody good? Okay. In terms of calculus, the 2 things that you do need to know are really the basics, okay? The 2 fundamental problems that calculus tries to address is understanding, number 1, the slope of the tangent line, which we develop a tool used to determine that, which is the derivative, and then the area under a curve, which we develop a tool to use that, which is the integral. And then the fundamental theorem of calculus says that the antiderivative and the integral are the same thing. That's calculus in a nutshell. In terms of the derivatives that we do, it is really basic stuff. What's the derivative of x squared? You probably already, that's probably 90% of the difficulty right there. Okay, we're not going to deal with any derivative of e to the x tangent of x raised to the 4th or some crazy stuff like that. We're not doing that. That's what Math 229 is for. We're not doing that in here. Same thing with the integration. If you can do basic integration, you're good. One of the nice things about your Casio and the TI-36 calculators, and to be clear, this harkens to a question that was asked, I think it was Monday during our first lecture, which is, am I a symbols guy or I'm a numbers guy? And more often than not, I'm a numbers guy. And the thing about definite integrals is that they have numerical limits. Definite integrals have a numerical answer, right? If you integrate x squared from 0 to 6, the answer is a number. It's not x, right? And your calculators can do that, and that's pretty valuable. There are a few instances, I'll tell you, where we are going to have some symbolic homeworks, but there's always a reason behind it. So when we first start doing centroids, I will probably give you one assignment where I have you derive a formula, and the reason for that is that in order to compute centroids, a task that engineers need to be able to do, you're basically taking a really weird shape and splitting it up into a bunch of simple shapes, and then you're going to a library of pre-derived formulas. And so I want you to understand those pre-derived formulas. So I might make you derive one of them, and once I know that you understand that, we'll just use those from then on. So again, there's a reason for it. I'm not just throwing alphabet soup at you because I'm mean. I promise you there is a reason. All right. Any questions? Let me tell you about your homework, and then I'm going to let you leave a little early. So your homework has really 3 problems, okay? The first problem is a dimensional consistency problem. Again, I'm going to give you a pile of junk and another pile of junk, and I want you to see if those 2 pile of junks are dimensionally consistent, equal to one another. And so it's a yes or no. The second is a right triangle. I'm giving you a right triangle, and I'm giving you some data, and I want you to solve for the rest of it, or whatever I'm asking for. The third is I'm giving you a triangle like this. And it's a similar question. I'm saying, what is the remaining piece of information? And so you got to figure that out. Honestly, the homework will open at 2 p.m. The last one opened at 1 p.m. because I wanted to pull it up here. But it will open at 2 p.m. And you'll be rocking and rolling. Now, I will tell you one thing before I let you go. So this one is also going to look like a test, but all things being alike, after this, it will be sort of more regular homework assignments. You do a problem, you scan it, and submit it. I'll go ahead and tell you, the reason for the sort of quiz assignments the way they are now is because my TAs don't start until next week, so I didn't want them to have a backlog of assignments. But after this, you'll have sort of a more regular assignment. Do the homework, submit it. One thing I will tell you, okay, with the scanned assignments, because I had this come up in another class because I do the same thing in there, is if you do the assignment and submit it and then realize, oh man, I made an error, you can fix it and resubmit for those assignments as well. You can keep resubmitting. The only difference between those assignments is you won't get an automatic grade. The TAs will have to go in and grade it. But you can keep resubmitting those assignments as well as much as you want. We'll grade the last one that you submitted. Sound good? Enjoy your extra 12 minutes of freedom. That's all I've got for you.
I was having some issues with the
Scanner.
scanner, yeah.
Okay, what's your name?
William Estrangelo.
Okay.
Yeah, I just want to let you know.
All right, I got you.
Thank you.
All right, no problem.
When will the schedule change take effect on Blackboard?
It might take a day.
Okay.
If you have an issue, let me know. But if like you miss this one assignment because of that, don't worry, you're fine.
Okay.
But from here on out, like starting Monday, it'll be on you. Yeah.
Professor, I just had a quick question.
Yes.
I'm part of the TEDx program, and our meeting ran a little late, so I was like 2 minutes late here, and I didn't get to be attended.
That's fine. Give me your name and I'll put you on here. That's fine.
Bella Schrader.
Okay. I will. I'll put you on here. That's no problem.
Thank you so much. Sorry.
No, that's fine.
Have a nice day.
You do the same. Feeling a little better about the trig? Hopefully.
You taught it to me in a day.
What's that?
You taught it to me in a day. Best of God. What calculator did you want me to buy?
What do you have one?
I have a TI-84.
That's fine.
Okay.
That's fine. You can keep using that. I don't have a problem with that. what I was telling people, so the reason for some of the calculators I mentioned earlier is because they're the ones that are approved on the licensing exam. But if you're biomedical?
I'm mechanical.
Mechanical. Okay, so if you're planning on taking the FE exam, then what's that?
What's the FE?
Oh, that's a good question. Okay, so you know how you get your learner's permit and then you get your driver's license?
Yeah.
Okay, so one of the things I mentioned in the beginning is that I'm a licensed engineer, so I'm basically board certified. And in order to get board certification, there are hold on, I need to stop that.